Hello. In this short video I will explain the main electrostatic characteristics of a powder coating spray system, the kVs and the microamps, the voltage and current. We will review how the charging system works, show what the declared maximum voltage and current actually mean for a spray system performance, explain which electrostatic system parameter is actually the most important to control and at which level, and also I will outline the path to future spray system performance optimization for maximum powder savings and the best finish quality. Here you see the main stated parameters of a powder coating spray system. The maximum voltage can range anywhere from 80 to 100, sometimes 110 kilovolts. The maximum current can be anywhere between 100 and 140 microamps, and the maximum powder output can be declared anywhere between 250 grams a minute for a Venturi system up to 750 grams a minute for a spray system utilizing the modern dense phase pump technology. The interesting thing is that the electrostatic parameters, the maximum voltage and the maximum current, are actually hardly ever achieved. And the maximum powder output is the function of the pump. But the important here is with which air volume is this powder output achieved. The volume of air defines the spray parent velocity, which in turn has the most profound effect on the application efficiency and on the ease of coating of complex product geometries and what is called Faraday cage areas. The Faraday cage is historically thought to be strictly electrostatic phenomena, but in fact it is very much an aerodynamic phenomena. When we don't control air turbulence inside a recessed area, this is when we start experiencing difficulties applying powder coating in the corners. Inside each spray system, there is a high voltage multiplier with a built-in resistor. Their design doesn't change much from one manufacturer to another. In fact, it's probably difficult to tell that the two multipliers shown on this picture are of two different makes. The high voltage multipliers of different suppliers can nevertheless differ in the quality of the components used and the quality of insulation and the potting, all of which affect their reliability and their cost. Here is an illustration of three main components of a high voltage multiplier. It consists of a transformer. The transformer receives the low voltage high frequency signal from a system controller. That signal typically doesn't exceed 30 volts. Which transformer then multiplies and turns it into several kilovolts, for example, 5,000 volts. This 5,000 volt is then further multiplied by passing through a diode cascade, giving us the maximum, for example, 100 kilovolt at the output of this multiplier. Before that voltage gets to the charging electrode of a spray gun, it is also passed through a resistor. That resistor is there to limit the maximum current produced by the spray system and also to limit the maximum spark energy to keep it below 2 millijoules required by safety regulations in order to ensure the fire safety of the system. We can illustrate what is happening in the typical powder coating system by drawing a simple electric circuit. There is a multiplier with a resistor inside the gun. That is our electrode number 1. And then we have a second electrode, which is our grounded parts. The quality of the second electrode is no less important than the quality of the first. Whatever we do to improve the charging system, to increase the kilovolts, to control the microamps, all of that can be in vain if the second electrode is of the inferior quality. If the reliable grounding of the product is not assured, no matter how good of a spray system one has, the process will not work. Well, to complete the circuit, we need to also draw the resistance of an air gap between the gun and the part. And this is shown here as resistance number 2. That resistance changes as we move the spray system closer or farther away from a product we're trying to coat. Once we've ionized air and created corona discharge, the space between the gun and the part is populated with millions of free-flying charge carriers. And the current starts flowing through this circuit. Well, as we said, the current flows through this circuit, and every time current flows through a resistor, a voltage drop occurs on that resistor. This voltage drop is equal to the current multiplied by the value of the resistance. What we just wrote is Ohm's law. Ohm's law was first published and discovered in 1827 by a German scientist, Georg Ohm. If we look at this equation, the resistance is primarily the resistance of the air gap between the gun and the part, and that we really cannot control. We can only keep the gun at a fixed gun-to-part distance, but this resistance is determined by the air gap and the volume of powder we've injected into this. So if we were to control the electrostatic parameters of the remaining voltage and current, we can control only one. The second one needs to be allowed to fluctuate. Once we've applied sufficient voltage to the tip of the gun and created a sufficiently strong electric field for the development of the corona discharge, the space between the gun and the part is populated with millions of charge carriers. And it's the flow of these charges from point A to point B, which is the current. So the current is the only direct measure of how much charge is created and passed from the gun to the product. So what about the kV? Well, not a single system on the market actually shows the kV at the tip of the gun. When you set the voltage to 50, 70 or 100 kV, you're merely setting the percent of the maximum output. We cannot measure the actual kilovolts at the tip of the gun in real life situation. So what is then the real kV at the tip of the gun? Well, that very question is answered when we look at what is called the load line of a spray system, which is the relationship between the voltage at the tip of the gun and the current load flowing through the circuit, thus the name load line. Here you see an example of such a load line for a spray system with the maximum declared voltage output of 100 kilovolt and the maximum short circuit current of 120 microamps. So what about the resistance? Well, we can show that as well on this load line. With these dashed lines are corresponding to the different gun-to-part distances. So for example, if the gun happens to be 10 inches away from the product or 250 millimeters, the line where the resistance corresponding to this gun-to-part distance intersects our load line will show us exactly what the voltage at the tip of the gun and what the current through the system will be. As we move the gun closer to the product, the current increases because the resistance of the air gap between the gun and the part gets lower, and the increased current creates greater voltage drop on the resistance inside the multiplier. So in this particular case, the voltage will drop to below 70 kilovolts, and the current will be just over 40 microamps. At an even closer gun-to-part distance of 3 inches or 75 millimeters, the current can go up to 80 or more microamps, and the voltage at the tip of the gun will drop to below 40. While the voltage at the tip of the gun actually follows the load line, the controller will keep showing us 100 kV. Therefore, when we control voltage, we actually don't control anything, because the voltage fluctuates and the current fluctuates. If one were to set voltage to a lower setting, for example to 60 kV, it would simply mean that we shift the load line from that maximum 100 kV output parallel to itself to the line corresponding to 60% of the output value. And here we also can see that the different actual gun tip voltage. So in this case, for a 250 millimeter gun to part distance, the actual gun tip voltage will be 50 kV, and the current might be anywhere between 13 and 15 microampere. To show you a real life example, here is a controller set to voltage control with the 100 kV maximum setting, and as the gun moves closer to the product, you will see the current go much higher, reaching the level of over 90 microamps when the gun is very close to the product. The level at which the development of deionization is guaranteed. When we control voltage, we do not control the charge. The charge is current. The current level can exceed the optimum if we allow it to change uncontrollably based on the changes in the gun-to-part distance. And the back ionization, which develops when we exceed the recommended charge level or recommended current level, is highly undesirable. With the onset of back ionization, the application efficiency deteriorates significantly, it goes down, and the finish quality does the same. You can see here an example of an application with severe back ionization of the product, and what you actually see is the powder jumping off the product. So what application efficiency can we talk about if we're spraying powder, we're trying to put it on, and it's actually jumping back? Once this happens, we have reduced powder application efficiency, we have inferior finish quality, and we also have compromised corrosion protection. Because if this happens to be a two-layer application, for example, we have already a primer coating, 𝗖𝗍𝗁𝗏𝗃𝗏𝗏 or a powder primer, or whatever primer that might be, which is already cured. Once back ionization develops, these sparks shoot through both coating layers. And when we put the product in the oven, if all these micro holes don't flow out completely, for example, the primer coating may not even remelt because it's already cured, then in the field, the corrosion failures will occur at exactly those spots where we had an intense back ionization. What about the maximum values that manufacturers declare for the equipment, the maximum voltage and maximum current? Well, the maximum voltage is right here, 100 kV. It's only possible in the open circuit condition when we have no corona discharge and we have no current. Imagine a gun suspended in the middle of a large room with no ground inside, including no ground at the back of the multiplier. Hardly a condition one would experience in real-life application. The same goes for the maximum current. The maximum current is short circuit current. It happens when the gun actually touches the product we're trying to coat. Well, needless to say, that will not work. So in fact, these two maximum values, maximum voltage and maximum current, never happen in normal operation, under normal operating condition. They're meaningless. I can further illustrate how meaningless they are by showing you these two different load lines. The blue one corresponds to a spray system with the maximum voltage of 100 kilovolt and maximum current of 110 microamps. The orange is representative of a spray system with 110 kilovolt maximum output and 120 microamps maximum current. So how does one get to having load lines of such different slope and shape? Well, this is achieved by using the select charge technology patented by Nordson in 1996. This technology allows us to shape the load line by altering the signal sent to the multiplier depending on the current feedback we want to achieve under the different load conditions with the different gun-to-part distances. This technology allows us not only to change the slope of a load line, but also to change the shape. And as one can see, for every gun-to-part distance, there will be absolutely different actual gun tip voltage and the current or the charge produced by the charging electrode and flowing from the gun to the part. So getting back to the load line comparison where we started with these two load lines, if we were to assume that more is better, then we would look at the specifications for a spray system and say, hey, this one with 110 kilovolts and 120 microamps definitely is better because it gives us more on both ends. Well, in fact, if you look at the resistance lines and if you look what the actual voltage will be at the tip of the gun, you can see that for a gun-to-part distance of 250 millimeters or 10 inches, both systems will have exactly the same actual gun tip voltage and exactly the same current. But for the gun-to-part distances closer than 250 millimeters or 10 inches, the spray system with the lower declared maximum voltage and current will have actually higher voltage at the tip of the gun. Does it mean it will be better? Not necessarily, because higher voltage can also translate, and it does translate, to higher current, which in many situations can be excessive and lead to back ionization. So what's the solution then? The solution is to control current. To delay back ionization, we must control and optimize, not maximize the charge. Since 1995, when Nordson led the industry in broadly implementing the current limiting feature on its spray system controllers, our focus has been on educating and enabling the powder coaters to optimize, not maximize the charge. So here's what happens when we work in the current limiting mode with the current limit set to 20 microamps. Instead of keeping the voltage at its maximum, the system controller will dynamically adjust the voltage to the level at which the maximum allowed current is not exceeded. Here the current is held constant, but the voltage will dynamically drop to maintain the current at the predefined level. On the load line, this will look like adjusting the position of this load line dynamically down or up in response to the changes in the gun-to-part distances. But once the current limit is set, that level of charge will be controlled. If we set it to even lower value, for example, to 10 microamps or even below, again, it just means that as the gun-to-part distance changes, the voltage will be adjusted by the controller faster. Historically, over the past 40 years, it has been shown that the optimum current level and the optimum charge is anywhere between 10 and 30 microamps for a vast majority of powder coating applications. When dealing with multi-layer applications, recoating, working with some dry blended metallics or special finishes, or with finishes which are highly sensitive to the development of back ionization, the current level below 10 microamps can be recommended. In the current limiting or charge control mode, all spray systems of the leading suppliers will have rather identical voltage at the tip of the charging electrode. Because once we enter into this current limiting mode, you can see that whether you started on the orange load line or on the blue one, in the current limiting mode, for most of the range of the useful gun-to-part distances, the actual gun tip voltage will be exactly the same. Slight differences can be measured only at large gun-to-part distances in excess of 300 millimeters. Doesn't mean that at this large gun-to-part distance, one system will be more efficient than the other. Not necessarily. At a larger gun-to-part distance, a number of other detrimental factors will nullify any benefit of having a slightly higher gun tip voltage. Because to spray from such a large gun-to-part distance, one would have to increase the spray velocity. At higher spray velocity, each particle will spend less time in the active charge zone, which is rather small around the tip of the charging electrode. Also, increasing the spray velocity will result in greater turbulence in the powder deposition area near the product surface, further diminishing any possible positive effect from having marginally higher voltage at the tip of the gun. So does it mean we're done improving the charge? And indeed it does. Historically, a 100 kV spray system operating at 8 to 12 inch gun-to-part distance or 230 to 280 millimeter gun-to-part distance will produce the charge level in the optimum range of 10 to 30 microamps. When we do not operate in this optimal setting, then controlling the charge, controlling the current flowing from the gun to the product will greatly benefit the application. Because remember, all those high voltage multipliers, they look and work exactly the same. And if ever somebody says, oh, my spray system charges the powder better, ask why. Most likely you will not get a clear answer. The current is the parameter we can accurately measure with most spray system controllers. It is the direct reflection of the amount of charge flow produced by the spray system and flowing, in most cases, from the tip of the gun to the product we're trying to coat. As I already mentioned, there is no technical challenge to produce a spray system delivering more than 100 kilovolts of the maximum voltage output. However, continuing to focus on the voltage is misleading for the industry and counterproductive for optimizing the spray system performance. So does this mean that we're done trying to improve the application efficiency and material savings in the powder coating system? Not at all. We still have tools at our disposal with the continuous optimization of the powder delivery technology, of the powder pump technology, in a way that allows us to achieve softer spray pattern, bring the powder to the products, as you can see in some of this video, with the low velocity, with minimum powder bouncing back, very high application efficiency, and very little airborne powder going into the recycle system. Additionally, significant powder material savings can be achieved through process control and very tight control of the applied coating thickness. With this, I thank you for sticking around for so long. If you have any questions, please send me an email and I'll be happy to get back to you. Thank you.